So, hello everyone, welcome to the first lecture on the deep learning, first chapter. So, I'm very happy that you could survive the boring video of logistics that we had before. Now, let's start to understand what is deep learning and what we do in deep learning, actually. So, maybe we could get a bit of motivation at the beginning. So, yeah, you probably have noticed that nowadays AI, and for those of you who are more expert, deep learning is a sort of unbeatable champion. So no one can win deep learning. And like you might have seen these kind of news that deep learning can outperform human being in image classification. It can just generate crazy human-like conversations. It can just win like the world-class chess players. And it could even solve problems which had not been solved before. Now, all of us have something to add to this list. For example, let's just get to know these stuff that we already talked about. So, for example, the problem of image recognition. Image recognition was a kind of old problem in machine learning. Many people wanted, I mean, it was one of the basic problems. They wanted to build a machine, a computer that gets the photo, and then it could say what is inside the photo, like it's a photo of a dog or a cat or something else. So it's pretty much started around 50s. But then it was always a kind of very poor machine that was designed initially, up to the point where LeCun came up with his idea of LeNet. It was basically a proposal. And after that, it somehow started to improve, but it was not a huge improvement. So in 2010, the project ImageNet, which collects lots of images with labels, like it says this is image and this inside the image is a dog or something like that. So it has millions of images with the labels being imported by hand. So this project started this contest called ILSVRC. So if you just take this ImageNet Large Scale Visual Recognition Challenge. So this was a kind of contest that they bring every algorithm proposed in the year, and they challenge them that if you want, you can just try out our data set and see what is your accuracy. And then it was 2012 at UofT, this AlexNet was proposed, and it somehow was a huge improvement. So a crazy breakthrough in the task of image recognition by deep learning. And after that, it was VGG by the Oxford people, Google LeNet, and then the ResNet recently, like in 2000, not that recently, but after 2015. So these networks started to just work like crazy. Like they were much, much better than any algorithm we could ever imagine. And nowadays, I mean, you can see that ResNet in 2015 was working pretty much perfect. And then nowadays we are just making deeper networks, and then you can expect that we are doing even better. So, but one thing interesting in that between was February 2015, when tech news agencies started to announce that first Microsoft and then Google claim that they have deep neural networks that could actually beat human accuracy. So if you give an image, a bunch of images, to a person and ask him to just look at the image and then try to say whether it's a cat, dog, what is inside it, then they're gonna have more errors as compared to those deep neural networks, which was a kind of breakthrough in the topic of image recognition. Another thing was like about human-like dialogue. So we always had been like a fan of having chatbots, some computer that could communicate with human being, and it could just produce some dialogues in response to the questions or dialogues of a human being, and then those dialogues are somehow meaningful and helpful. So things like chatbots started to be commercial on many web pages, but you do know ChatGPT, which is, for the record, is like the fastest growing software in the history. And I think it reached 100 million user within a very short course of time. So ChatGPT is nowadays pretty much behaving like a human being. So you can ask it anything and it would answer you very meaningful answers. Another thing is chess. So chess playing was again one of the very first problems in AI. So many people assume that if we are talking more about artificial intelligence, then when the computer needs to do something intelligent, and chess is something intelligent. So probably we need some computer, or it would be great if we have a computer which can play chess. Actually, Alan Turing, the legendary guy in computer science, he actually started with his program in 1951, which was a program that could play chess. And then from then on, many people started to work on developing computers which could play chess. And one of those companies was IBM. So in 1989, they were first somehow self-confident that they could play with a real chess player, a world-class champion, who was Garry Kasparov. And Garry Kasparov could beat the IBM machine, which was called Deep Thought. After that, IBM developed the Deep Blue machine. And again, Kasparov could defeat it on 1996, so 7 years after the first try. But the year after 1997, the Deep Blue machine could finally defeat Garry Kasparov, which was a kind of, say, historical moment. And those algorithms started to develop over and over. And for the record, or as recorded, 2005 was the last time when a human being could beat a computer. And after that, no human being could beat any chess playing algorithm. And those algorithms started to develop and they started to compete with each other. So they started to just match against each other. And one of the very promising algorithms developed by DeepMind was in 2017 called AlphaZero, which was a last chain in the sequence of algorithms developed for different board games. First one was for Go game, and then the final one was for the chess game. And AlphaZero was very promising because it was a deep learning based algorithm. And then this algorithm just took 24 hours, one day, to get trained. And then it could defeat a very powerful chess engine. So it was crazy that within just one day of training, 24 hours, one algorithm could get into one point that it could defeat the best chess player known at that time. So yeah, and from then on, there are lots of other algorithms which are trying to just improve the quality of this algorithm, again, based on deep learning. And this was really promising, very wonderful. And for many people, like 10 years ago, it was a kind of dream. Nobody could buy it, that it happened so quickly and so promising. Another thing that machine learning has helped a lot, or deep learning has helped a lot, is the neural machine translation, or translator machine. So many of us know about like Google Translate. Many computer programs which do online translation, they get either voice or text, and then they translate it into another language. And those computer programs had been a kind of topic of research for decades. Actually, starting from 1950s, that human being wanted, I mean, many people, many scientists wanted to design a computer or basically algorithms that could translate everything in online fashion. Like I am talking in English and then it just gets translated into another language. So this was a topic for decades, and around 2000s, statistical machine translation became kind of dominant approach. It was good. So Google, for example, started to launch its own translator, Google Translate by SMT. But it was 10 years after, or maybe more than 10 years, that the idea of neural machine translation or doing the translation based on or by means of neural networks or deep learning started to be seen as a kind of great potential. And then it didn't take that much of time. So it was 2015 when the first one in a kind of say commercial fashion, large scale fashion, got launched. And 1 year after that, Google also adopted neural networks for translation. And the improvement was noticeable. So you could notice how improved the translation got after the introduction of these neural networks into the machine translator by Google. And many companies started to just get launched based on this idea. So in 2017, DeepL company launched, which is one of the big companies, translation companies nowadays, and lots of other things. I mean, you can find lots of translators based on deep learning. So Gloom gonna kick in inside this part of the slides, and then he gonna ask me this kind of question, which I imagine is maybe in a very deep part of your mind as well. That okay, these are nice examples, but what is exactly this deep learning? And I could just get the definition of deep learning, copy it from somewhere on one textbook, and bring it here. So deep learning refers to a subset of machine learning that uses deep neural networks to execute a given learning task. Well, it sounds like a fancy definition, but I do believe anyone, including Bloom, would ask such a question like, okay, the only thing clear in this sentence is that there is something called machine learning, and deep learning is somehow like machine learning, but more specific. And there are things like neural networks. But first of all, what is this machine learning? And secondly, what are those neural networks? And what exactly it means that we have deep neural networks. So what is a deep version of a neural network? And the next thing is that what do you mean by executing a learning task? What is a learning task? So it's a kind of high level definition, which is not very useful to start with. So this is why I'm going to go through some details of machine learning. We start with something a bit basic. So let's start with the machine learning. And again, I am just copying the definition you could find in the deep learning textbook. So what is machine learning? So a form of applied statistics with increased emphasis on use of computers to statistically estimate complicated functions. So again, a bunch of words which are very fancy and definitely meaningful to people who are working in the area, but they are not very clear for some beginner. So let's make it a bit more clear. So let's put it in some simple words. Machine learning is a kind of, I would call it a kind of alternative approach to solve a problem that we might not be able to do it analytically. So if we got a problem, we have a bunch of variables given to us, and we want to calculate something out of them, then we have two different approaches. One of them is to do it analytically. The other one is to do it in a data-driven fashion. And machine learning is basically the area where we try to design some sort of good data-driven algorithms. So this is somehow a very intuitive definition of machine learning, but I do know that it is not yet very clear. So the best thing is to just have some sort of very dummy example. The dummy example that I considered in this part of the lecture is the motion of a projectile. So a projectile, a simple ball, say for example, is located on some height. So I have just assume this y-axis is showing the height, and then this x-axis is showing the ground. And I am locating one ball here at location h. So there is a height h from the ground. Now there is one horizontal velocity v that initiates this ball. So I am just initiating the ball to move with velocity v. And when I do that, this ball gonna just move on a kind of curvature of this form, and then it hits the ground at some distance d from the origin. And now the question is, what is this distance d? Okay, this is a kind of simple question that you could got when you were high school. I do know for many of you, and also me, the analytic solution, I'm sorry, the analytic solution is not very clear at the moment because you might have forgotten the details. But when we were high school, all of us could solve it very clearly using the motion laws. So we are going to do this right now together once again. So just to recap what we had before. And then we try to also solve it by the machine learning approach. So by the data-driven approach, and then we see the difference. So let's start first with the conventional approach that we had in the high school. So when we want to do the calculation here, we assume that this guy is moving with the speed v. Just for the record, I do not expect you to remember anything of that. So this is why I made the next slide. But you really don't need to worry about that. It's nothing that you're gonna use it in this course at all. It's just to have some sort of simple analytic problem. So when we just kick this ball at height h, it's gonna move in the x and y page, or through the x and y axis. So at time t, it's gonna be at the on the x-axis, it's gonna be at some distance v times t, and on the y-axis, it's gonna be on some distance minus g half t squared plus h. And what is this g? That is the gravitational acceleration, so approximately 10 meter per square second. So what you can see here is that as the time passes, so this negative term is increasing. This is because the gravitational force is just taking the ball down. And then the distance on the y-axis is going to shrink up to the point where it hits the ground, and it's going to be exactly 0. And that moment is actually when we have this first negative term being exactly equal to this value h. So if I want to find the time, the moment when the ball hits the ground, I'm going to put y equal by 0, and then I calculate this t0. This is the moment when the ball hits the ground. And at that moment, the ball on the x-axis has passed this distance, and this is exactly the distance d that I'm looking for. So first of all, I put y equal by 0. So t0 gonna be just, I need to solve this equation for t, and this is gonna be this term. So a square root of 2h over g. And then after that, I can put t to be t0 in this expression in order to calculate distance. So the distance is gonna be d equal by v times this t0. And just to present it very compactly, I'm going to define this square root of 2 over g, which is a constant, approximately 0.45. I'm going to call it to be gamma, and then the distance d is going to be gamma times v, the speed of the ball, the initial speed, and then square root of h, which is the square root of the height of the ball starting when it was kicked on the y-axis. So that is the analytic approach that we would have done if we were high school students. We would conclude that the distance d is this expression, and how we do it, we actually do it based on some pre-assumptions. First of all, we assume that we do know the Newton's law, we trust them. They are actually correctly describing the motion, and we do know them, so this is one thing that we need. And the other thing was that we could solve the problem in a feasible time. So it basically means that, for example, here, when I wanted to calculate this t0, or putting y equal by 0, I wanted to solve the equation for t, it was an easy thing to do. It was not something very complicated. But in practice, this is not always the case. So it might be the case that, for example, I don't know the exact physical law that describe the relation between V, or my output, and the inputs that are given to me. One example is, for example, that all of us know that smoking is something related to getting cancer. So if we smoke more, we probably increase the chance of having cancer. But there is no exact physical formula right now at this moment that describes the chance of getting cancer with the number of cigarettes in terms of the number of cigarettes we have smoked. So there is no exact physical description, or say analytic description, of the relation between these two related variables, chance of getting cancer and the number of cigarettes we are smoking. We do know there is a relation here, but there is no clear formula for that. So in that case, we don't have actually the laws that describe the relation. One other case is that we might have some sort of laws here, like what happens in thermodynamics. But those laws, if we really want to use them in order to find out the variables we're looking for, they're going to be super complicated. For example, we're going to end up with an equation with 10 to the power 32 variables, which we cannot solve it with our computers at the moment. So if this is the case, then we can actually not use this analytic approach. And this is where we are going to look for some machine learning approach or some data-driven approach. So how does ML approach look like for this particular dummy problem that we had here? So assume that we didn't know like the equations, the motion equations, or for example, we are not able to do the computation, whatever. For any reason, we are now going for the ML approach. So what we do in ML approach, we first of all try to do the experiment for multiple times. So say, for example, we do the experiment for I different times, and in each time we start the experiment with different velocity and different height, and then we look at the distance at which this ball is hitting the ground, and then we go and measure that distance. So we collect all of those data in one set. We put the distance and also the corresponding velocity and height for every single experiment. Now, the next thing that we do, we assume that this distance is somehow related to that v and h in some predefined manner. For instance, for example, we just assume that d is related to v and h in this form. And as we already have seen, this is not a correct relation. So this is actually a wrong relation between V and H. It is true that it's describing proportionally the right proportion. So for example, like we know if V increases, D increases. If H increases, D increases. This is correct, but the exact relation is not correct. But as I said, we assume at this point that we don't know the exact relation. So this is what we assume. We assume that D is in this form, and also we assume that this W0 and W1 are some free parameters that we can play with. Now, if we are able to play with these two parameters, what we are going to do, we are just going to play around with W0 and W1 and find some optimal value for each of them, such that this predefined model that we consider here very closely matches our experiments. So in other words, like for most of the parameter or input outputs that we have calculated and put in our set of experiments, for every single experiment that we have done, this model or this expression that we have considered here gives us pretty much the same value for D. We are going to find those W's. And if we find those W's, then we use this model in order to just give any new value for D if we get a new V and H. Now, how we can find this W0 star and W1 star? Well, we can be a bit naive at the beginning and we could say, okay, we want this model or what we have assumed as the relation between D and V and H to exactly recover all of the experiments that we have done. It means that for every experiment, the distance is exactly this W0 star times the velocity plus W1 star times the height. So we go ahead and search for those values of W's. And if you want this to happen, by this sign, I mean that I want this to happen. I don't know if it happens or not. Then what we need that the difference between D and this guy on the other side, as I showed it here, to be exactly 0. This one being 0 is equivalent to its square being 0. So there is nothing specific here. And if I want this to happen for every single experiment, then I need the summation to be 0 as well. So here, if I end up with some non-zero summation, it means that it is not happening for one particular experiment at least. But if it happens to be 0, then it means that for every single experiment, my D is exactly W times the V value plus W1 star times the H value. So this is what I want, but I think for many of you, this is very clear that if I increase the number of experiments, if I is more than 3, for example, it's not going to work because say we have 3 different experiments, it means that we have, I'm very sorry. So we have 3 set of equations here, and we have 2 variables, W0 and W1, which necessarily does not have a solution. So in that case, we could run out of solution. So the solution might be empty, simply. So if this is the case, then what we are going to do? Okay. Probably most of you have done it before in the physics or chemistry lab. What we do in that case, we just calculate this term, this residual sum, and we try to minimize it. We try to make it as small as possible. So we actually find these values of W in a form that this term is actually minimized. So we can look at it in a different way, a bit of different way when it comes to machine learning. We can say that we have a kind of loss function. So the loss function is actually this term, where we are free to choose the value of W's. So here you see this loss function is exactly the term that we have above, the same thing. And we are free to choose this W0 and W1. And what we do, we just try to minimize this term, this loss term. So we're gonna find W0 and W1 star, such that this loss term is actually minimized. Okay, So if we do that, then we get some term W0, W1 star. And if we use this expression here, then we could say pretty much for every experiment that we had done, this D is approximately equal to the other term. Yeah. And then we could take it for granted. We could say if you give me a new velocity in h, then I can calculate the approximately, of course, the horizontal distance using this expression. Okay, this is the machine learning approach, and we can, based on this dummy example, we can give two intuitive arguments here. First of all, we are pretty sure that this expression for D given by the ML approach is not accurate because the term or the relation that we have written here is not exactly what we get in the analytic form. So it is not accurate, but if we increase the number of experiments, if we do a lot of experiments, then probably we'll find the values for these W's that give us a sort of accurate approximation here. So we do not get the exact solution, but when we have a large number of trials, then we might get the performance of this approach improved. So these are two things that we could say in an intuitive manner, and this is actually something very correct in general about the machine learning approaches. So now let's start with this example and try to project everything into a more general form. So when we are talking about a machine learning approach, we always have a problem, which we cannot probably solve it very easily, at least by the analytic approach. And because of that, we are going to use the ML approach. And when we are doing the ML approach, we are going to use three main components in the problem. The first one is the data set. For example, for the dummy example, we collected the speed, height, and the distance. And we also assign them together. We said, like, for this V and H, we have this value of D. So this is what we call it the data set. And we also had something called model. We assume that this distance D is somehow related to the velocity in H in this form. Of course, it was not a very correct form. It was actually analytically a wrong term, but this is what we did. Because say we are really using ML approach, then we have a problem where probably we don't know exactly what is the relation. The only thing that we could say is that, yeah, increasing or decreasing this value of V or H, it could how it would impact D in the best case, actually. And in that sense, we need to have a model that describes the relation between input and output. And this is what we call it model in machine learning. Like in our dummy example, we consider this linear model, but we could consider different models. And the last thing was loss. So we actually were somehow aware that this model is not going to work for us perfectly fine. So it's not going to be like very accurate. And what we are going to do, we are just going to match this model in a way that it gives us the minimum difference to what we have observed in our data set or what we had measured, these values of D. And we calculated it by this particular expression in the example. So we basically just calculated the sum of the residual terms. This is one approach. We could have chosen different approaches to calculate this loss. But at the end of the day, when we fix the loss function, the term that calculates the loss for us, then we can somehow manage to find values for these terms W, so that the model fits the data set very perfectly. So these are the three key components that exist in any machine learning problem. So any machine learning problem would have data set, model, and loss. And what we are going to do now, we are going to just look at these components with more details in this chapter. So let's start with the data set. But before I get into the data set, I would like to recap a bit about the vectors and matrices. So in general, about the linear algebra. So throughout the lecture, we are going to always deal with column vectors. So we're always going to have some column vector, and we show the column vector with boldface small letters. So as you can see here in these slides, if you see me writing on the board, then because I cannot distinguish between boldface and the normal face, so I'm gonna just put an underline. And when we say a vector, the vector is simply a column vector. And if I want to make it a row vector, I simply put a transpose on top of it. So this is going to be the notation that we are going to do. So always we consider by default a column vector. And if we need to have a row vector, then we are going to use the transpose notation. This is one thing. And the other thing is about the matrices. So in general, when we have n times m matrix, we mean that we have n rows and m columns. And we can look at that matrix as a collection of m different column vectors. This is one way of looking at the matrix. Or we can look at it as n different row vectors. So both of them are right. Yeah. And depending on the calculation that we are dealing with, it might be easier to consider one of these points of view. We show the matrices with boldface capital letters. This is important. So a boldface in this form, the capital letter, it means a matrix. And also it's useful to just define the inner product. So the inner product of x and y, I'm going to show it by xt, the row vector, multiplied by y, which is the column vector. And it's going to be the summation of entries being multiplied. So this is the inner product. And it is easy to see that it doesn't really matter which one is inner producted with the other one. It's going to be the same term always. We also have the outer product. So if I multiply a column vector with a row vector of the same dimension, of course, here we don't need them to be in the same dimension. But for the inner product, I should indicate that they should be same dimension. But okay, I have written it here, so no worries about that. But if we have two vectors, x and y, we can then do the outer product as well. So we can just multiply the column vector with the row vector and gonna be a matrix. And again, it's easy to see that if we just exchange the order of the vectors, then everything gonna get transposed. Like y transpose times x gonna be the transpose of this matrix. Then the last thing is about the matrix vector multiplication. So it might be the case that we multiply matrix to a vector. I mean, throughout the semester, throughout the lectures. And if we want to do it, we can, I mean, you can always consider it in one of these two forms. Either you can assume that, or you could look at this matrix to be a collection of the column vectors, and then we are actually doing a linear combination of them, and the coefficients of this linear combination are those entries of the vector. This is one approach. And the other one is to just look at them as a collection of inner products. So we look at the matrix to be a collection of row vectors, and then the product gonna be the inner product of every row to this vector. So as I said, these are very basic stuff. I do know, all of you know it. I'm just repeating them to recap, first of all. And secondly, time to time, it might be one of these point of views might be useful to just present everything with. So just to make sure that we are both on the same page. Okay, now let's get to the data set. Let's see what is a data set. As we tried it in our experiment, or in our dummy example, the data set was a collection of experiments or data points. Every single data point is one of these pairs, as you can see here. So one item in the pair is the input value, is what we set. For example, in our experiment, we set the velocity and age. And the other one is something that we are calculating or measuring after that. And this calculation is definitely depending on those other terms. What we see here when we have data set in this form, it is what we call it a labeled data set. It means that or entries here in the data set or elements of data set, they are pairs. And each pair contains one variable which depends on the other one. So basically, they are describing the input-output of one function, which we don't know. And the output of the function is also given to us. This output of the function, we call it the label. So when we have a labeled data set in general, we have, for example, one vector as the first item in the pair, and we have one scalar, which is the label of that input point or that vector. So we can think of this label here as the output of a function if we give this value to the function. And what is our learning task? Our learning task is to just find out what is this function. Maybe we cannot exactly find it out, but we can at least approximate it. So we could say approximately this function gives you a value of that if you give another input to the function. Now, as I said, so the learning task here in this problem is very clear. So when we talk about the learning task, we basically mean what we are going to approximate, what we are going to understand from this problem. And in this particular example, we are going to understand the relation between the input and output, or in other words, to just learn what that function, which we don't know it exactly, how does that function look like, or approximate it at least. This kind of problem with this kind of data set is what we call it supervised learning. It means that we know the label, we know the output of the every single input, and this is somehow looking like we have a teacher, we have a supervisor who knows that function, we don't know the function, and he is just trying different inputs to this function and gives us different label, different outputs of the function. They give us that value, or those set of values, and then based on that, we are trying to just predict or anticipate what the function would do at another point. So this is the kind of problem that is supervised by having the label. This is why we call it a supervised learning problem. But if we want to just define it simply, a supervised problem is the problem where we have the input points and also the labels, the outputs of the function. The main focus of this course is, of course, on the supervised learning. So we are going to touch other topics as well, somehow, but the main focus or the main examples we are going to solve in this lecture or in this course entirely gonna be focused more on supervised learning because they are the main tool. I mean, when you know supervised learning, then the remaining things gonna be much easier for you to understand. So it's the best point to start with. So you might wonder, you might have this question like gloom that is it possible that a data set has no labels? And the answer is that yes, it could happen. Actually, this is the problem which we have in unsupervised learning, where we have some bunch of data points in our data set, but we don't have any label for them. And you might wonder, I mean, how is it even possible to have such a data set? What is the learning task in that case? What do we know or want from that data set? I mean, for label one, that's clear. We need to know the function. But what can happen if we have such a data set? Well, in that case, usually the learning task is something that we call it unsupervised. So this is why we call this kind of problems unsupervised learning. So you are not given a specific function, target function to learn or to understand, but rather you are asked to do some sort of understanding from that data. Like, for example, if you could just extract some features from the data. Okay, how can we do it, or what it would be really in practice? So let's have a simple example, which is quite well known in this topic. So say I have some data which is coming from a natural process, like my voice, you are listening to it, you can sample it, the wave of the sound waveform every couple of minutes. So you can collect, say, 1,000, 100,000 of samples from every couple of minutes of my voice. And then this is a natural process. So from time to time, it's going to be different. You can collect all of those samples inside a data set. One thing that you do know is that these samples or these vectors, which are very large vectors, for example, as I said, like in the order of 1,000, even though they are very large, but they are actually summation of few principal vectors. Like this x is of dimension n. So if I look at it as a column vector, as we talked before, it has n different entries. And this n is a very large value, but I do know that it is the summation of some a, this is a scalar, multiplied by vq. And these vectors v, they are again n-dimensional, but there are only few of them. So if we consider this expression here, first of all, let's try to use our linear algebra knowledge to just present everything compactly. So I can put this v values in a form, v vectors in a form of a matrix. So v1 is the first column, v2, and we go on till vq. It's gonna be a n, the number of rows, times q matrix. And then I can collect all of these coefficients, a1, a2 till aq, in a vector of dimension q. If I multiply this matrix now with this vector, I'm going to get back to this expression, which is my data point x. Okay, let me call this matrix here the matrix V and call this vector to be vector A. It means that I can write down my x, my vector x, in this form. What is the cool part about this is that this vector x, which is of very large dimension, we said, could be represented by one matrix V, which is still like having so many rows, but this is fixed. And then the A vector is of very, very small dimension. So we can actually reduce somehow the dimensionality here if we know this matrix V. If I know matrix V, then I don't need to really save X. I just need to save A. And whenever I need X, I can just multiply that small a to V, and then I get the big X. Cool. But the issue is that we don't have any access to this matrix V. This is the problem. And this is, again, an unsupervised, unsupervised learning problem. Why? Because here I do know this knowledge that X is depending on some A, which I don't know what it is, in the form of a vector matrix product. But the issue is that I don't know that matrix. Some of you might have heard about this problem. They call it, or this type of matrices, some people call it dictionary. So we have a dictionary. If we have it, then we don't need X actually, we just need the translation A in lower dimension. And then we can always get back to X by these two. But the problem is that I don't have any of them. Yeah. Now, what I can try to do, if I collect so many x's, I can try to see what could be this matrix V. Yeah. So here I got a problem whose data set is of this form. It is totally unlabeled. I don't have any label for my data points, but it is still a learning problem. And this is unsupervised because I actually have no label in my problem. So for some of you might be who had lectures in machine learning, you know that this problem is what we call a dimensionality reduction. And principal component analysis is one of the classical solutions to this problem. There are also other examples of unsupervised learning problems or data sets without labels. For example, in the problem of clustering, which nowadays is being commercialized by Amazon and Google and other engines. We also do unsupervised learning in that cases. But as I indicated, supervised learning is the main concern of us, at least halfway through the semester. So we don't need to really bother ourselves with unsupervised learning for the moment. There are some other variants in terms of data set. For example, we could have a semi-supervised learning, like we have a data set which has bunch of data points with labels, bunch of data points without label. This could be a case. There is also other class of problems, which we call it reinforcement learning. So there exists one client, and this client is actually doing actions, and depending on the action, it gets some feedback, and those feedbacks actually improve or increase the size of or complete the data set. So the data set is somehow growing through time. And the best example of this case is the chess playing game. I mean, when you play chess, I mean, depending on the move you do, I mean, there are a bunch of choices for you, and each choice would lead to different penalty for you. So this is a problem which is essentially a bit different from this kind of classical problems. It is definitely related very much, but it needs some modification. One thing that I would like to just indicate here as a side note is that we are going to just briefly touch the unsupervised learning as well, but our main focus is going to be, for the moment, unsupervised learning. And that reinforcement learning is somehow beyond the first course in deep learning. So this is going to be a topic for another lecture, which hopefully we're going to have it in next summer. So now that we know the meaning of data set, and also we know what is supervised learning problem, since that we are focusing on such problems, let's just make it easy for ourselves. And then we just consider the data set to be of this form. So our data set is actually the collection of data points with labels. And what we want to know, we want to just learn the function that maps these vectors, x or x vectors, to the labels. If you want to do that, we need a model. And what is a model? Simply speaking, it's a kind of parameterized function. So a function with parameters. And those parameters, we can tune them freely. We can change them freely. So, for example, in the dummy example we had, we assume that distance is related to velocity and h in this linear form. And we call it linear. Why? Because I can write it down in this form. I can first start it with writing it down as an inner product of vector w and this data vector. And then I can look at it in this form. So it's actually a linear function in terms of x, because it's just the product of x with one other vector. And just as a reminder again, we call such a term to be a linear function in terms of x. So y here is a linear function of x, but we also have a affine function. An affine function is simply the same thing, which is not passing through zero necessarily. So if I put x0 here now, I could have something non-zero. And this is why we say that the linear function or affine function is the extension of a linear function, which can actually have a bias. It could just pass, it could simply not pass through the origin. Just to make it clear, because we are going to use these two terms quite a lot. Also, we can extend the idea to a higher dimension function. So we can assume a function that is getting x, which is multidimensional, say, for example, n-dimensional vector, and returns one output y, which is again multidimensional, say m-dimensional, which could be different from n. And again, this is going to be a linear function, and this is going to be a vector valued affine function. So in our dummy example, we consider the linear model, which means that we consider D or our label to be W times X. But we could have considered, for example, a affine model. Yeah, we could also consider a bias for it. Or we could just go ahead and consider like a polynomial term or a polynomial model. It means that we assume that when I get X, I should calculate all polynomials or all powers of X, like X squared, X cubic, and so on till X to power P. And by this notation, X squared, I simply mean that I am just squaring every single element inside the vector. I could consider all of them, and then I just let different vectors W1, W2 to WP just getting multiplied by my X. And then I also add a bias. So this is a more general model as compared to this one, because if I set P equal by 1, then I'm going to get back to this model. So I could have considered the polynomial model. I could have considered actually a crazy model like this one. And I'm sorry. And you could simply see that this model is actually fitting the analytic model. So there exists one W1 and W2, which exactly recover what we calculated analytically. But anyway, I could have started with assuming such a model for my label, for my distance. So then the point is that all of these models are potentially something that we can use. And how we can do it, or which one we should choose, this totally depends on the problem that we have. But the key point here at this point is that when we are talking about a model, we simply talk about a function like this one, which has some parameters. This, for example, here, W1 and W2. And what is our goal? We are going to find these W's or those parameters in general in a way that our model is fitting the data set that we have in a best form. Then we somehow say, okay, since it is fitting our data set, we try to extrapolate everything to other data points as well, and hopefully it approximately work as well there.